Hello and welcome to our oral presentation for our paper, Who's Waldo? Linking People Across Text and Images. In this work, we present a new task, dataset, and method for person-centric visual grounding. I'm Claire Yu-Qing.
And I'm Apoorv Khandelwal. Now, I'd like you to take a look at this picture featuring Australian football players Caleb Marchbank and Matt DeBoer. After reading the caption and assuming you're not already familiar with them, can you tell me who in the image is Caleb and who is Matt? Caleb is kicking the ball away from Matt. For humans, it's easy to associate what's happening in this picture with what's described in the caption. But for AI models, this is a difficult task that requires complex visual reasoning skills. In this paper, we explore how models might begin to tackle such tasks in the context of difficult real-world examples. This problem is an example of visual grounding task. Visual grounding is a vision and language task in which the goal is to localize objects in images given free-form textual descriptions of those objects. In the example, there is an image and a corresponding description that says a girl on the left. In this case, the visual grounding task is to compute a bounding box in the image corresponding to this text. Visual grounding has applications in many areas, including image captioning, visual question answering, and instruction following. Several datasets exist for the task of visual grounding. These images are from the referring expressions datasets and are annotated with short phrases characterizing objects explicitly by categories and immediate visual or spatial attributes. The rightmost image is from Flickr 30K entities, which presents sentence-length captions, but still has similarly direct language. Such direct textual content weakens the difficulty of the task, as models can partly learn to solve visual grounding by simply learning priors over object categories. These captions also only have limited descriptions of inter-object relationships. Furthermore, these previous datasets were annotated using Amazon Mechanical Turk, which may induce significant biases as the distribution of captions is heavily influenced by the formulation of the task presented to workers. As a result, these captions you see here don't quite resemble realistic captions that you might find on the internet. In contrast, the example we showed at the beginning of the talk is an example of a real-world image caption pair and is centered on interactions between people. In images typically found online, people are described by name, for example, rather than just a man or a woman. And the captions are more descriptive, often describing interactions between multiple people. Again, here, Caleb is kicking away from Matt. Accordingly, we present a new task called Person-centric visual grounding. Our goal with this task is to move beyond localizing named objects, which can reduce the problem to simple categorical object detection. Instead, we want methods to reason primarily about context and interactions between objects. We define person-centric visual grounding task as follows. We are given detections of people in images and masked mentions of people in text, and wish to find correspondences between these mentions in text and the detections in the image. We mask the names in the text with a generic name token, so that methods can't learn priors over the surface forms of names. Here's what a potential method sees. The person detections in the image are labeled A, B, and C. The method must associate each of the two name tokens in the text with one of these detections. In this example, we see that A is kicking the ball and C is pursuing him. So the first mention in the caption must be A, and the second is C. This is a complex visual reasoning task because we must understand what is the underlying activity, kicking, determine who is kicking and who away from, and which people are not mentioned at all, B in this example. Alongside our task, we also present a benchmark dataset called Who's Waldo. From a collection of people-related images available freely on Wikimedia Commons, we curate a high-quality dataset of 270,000 image caption pairs. Here's an example of one image caption pair, which, as we can see, involves multiple people and features a detailed textual description. We do need to do some processing to create our dataset from raw Wikimedia data. For each image, we run a whole body person detector to produce a bounding box and 130 key points for each detected person. For each caption, we need to identify spans of text corresponding to people's names and cluster these names so that we know which mentions refer to the same person. We run named entity recognition to identify person entities and co-reference resolution to determine which person entities refer to the same person. We also need ground truth links between mentions and detections. We can generate such ground truth links by virtue of additional information in Wikimedia Commons. Our images are often associated with the Wikipedia profiles of people pictured. We can then generate a set of reference faces for each individual and compute their similarity with faces from image detections. As visualized, we can then produce a ground truth corresponding from this matrix. Our processed data now contains images and their captions, along with clusters of name mentions, people detections, and ground truth correspondences between these. Here are a few more annotated samples from our dataset. We color detection boxes in the image with the same color text as its corresponding ground truth reference in the text. As these examples show, our dataset spans a wide variety of situations and interactions. Next, we introduce our approach for linking people and text and images using our dataset for training and evaluation. Our technique uses a visual transformer-based model.
Recently, many works have trained and applied transformer models for a variety of core vision and language tasks. These models can be fine-tuned for several downstream tasks, such as visual question answering and visual grounding. In our work, we embed image detections and caption tokens through a visual transformer model. We then compute similarities between embeddings of detections and name tokens from the caption, from which we can estimate box name correspondences. We supervise and regularize this model with several losses on the box name similarity matrix. Given known ground truth links, we apply cross-entropy losses, row-wise and column-wise, over this similarity matrix. We observe that when an image has only one detection and its caption has only one name mentioned, these entities are highly likely to refer to the same person. Accordingly, we can apply a binary cross-entropy loss for positive and negative box name pairs in this case, where negative pairs are constructed from other images in the batch. Additionally, we observe that image detections that are small or blurry are unlikely to correspond to a referred person in the caption. We apply another binary cross-entropy loss to ensure such detections have low similarity scores. As part of our dataset, we include a test set of 6,700 image caption pairs exclusively featuring people who are not seen during training. We evaluate several recent visual grounding models on our test set, including a weakly supervised framework and several supervised frameworks. These models all struggle on our person-centric visual grounding task, and our proposed method significantly outperforms them. We also evaluate the performance of several heuristics to better illustrate the challenges and biases in our data. As illustrated in the graph, the L2R largest heuristics, which performs a left to right ordering of the largest detections, yields relatively strong performance, although ours still outperforms it by a significant margin. Here are several samples from our test set, along with the predictions of our model, covering a diverse range of interactions. On the left, person A is going over instructions with person B. In the center, person A is behind person B, who is the goalkeeper. And on the right, person A, who is an astronaut, presents item to person B. Both the left and right examples do not follow a left to right ordering, meaning that the person that is mentioned first actually appears on the right in the image. Yet our model can still correctly link between the text and image. We also perform a comprehensive ablation study, ablating different features provided to the transformer model, as well as our loss objectives. The impact of dropping textual features while retaining only position features and special name token was the most significant, with performance dropping by 12.2%. Training without our estimated ground truth resulted in nearly a random guess, which is aligned with the low performance obtained using the weakly supervised baseline. To better understand what the model is learning, we also ran a detailed analysis of the role of the number of referred people, the number of detected faces, the occupations of the mentioned entities, and the number of identity occurrences. Please see the paper for more details. Finally, while we show encouraging performance on our new task, there's still ample room for improvement. Most importantly, some interactions are more complex and also less frequent in the data. For example, understanding what blocking means in soccer. On the other hand, there are also limitations in our dataset, as some captions are insufficient to produce meaningful links. Since the model simply does not have enough information to output a mapping, it produces a left to right ordering, which is not necessarily the right solution. In summary, we present a task, a dataset, and method for linking people across images and text. We've shown that by masking out names of people, we force methods to not memorize the appearance of specific individuals, but to understand contextual cues and interactions between multiple people. Additional details and the link to request access to our dataset are available on our project webpage. Thank you.